Sorry, I accidentally closed it. Bear with me, please. So, okay, sorry, where was I? So, yeah, so that's the relationship between, that's joules. That has its own unit. It's 8.31, and that's the temperature in kelvins, not in degrees, but in kelvins. And they'll give you the value, and we'll lineate it sometime else. But you'll have to use natural logs to lineate it. lnk equals lna minus ea over rt, and then you'll have to separate ea over r on one end, and then 1 over t2 minus 1 over t1, and then you'll have to take the temperature gradient. So the plot is between activation energy and temperature, not necessarily k. So this is why this equation is feared by A-level students, because it's a bit multifaceted. It forces you to learn natural logs, understand gradients a little bit more deeper, and also realize that the graph is being drawn between these two and not this or this or this. So I've just written it as inverse because it saves me a lot of time and I wouldn't have to put a forward slash here. So again, I mean, we know that everything's coming from collision theory, Brownian motion of Robert Cook. So the postulates, Cook's postulates and whatnot, and the pollen theory. So, it's affected by temperature, pressure, concentration, surface area, and then speed of injection, rate of interaction, and then the style of collision, glancing or head-on, that also determines it. And so this is, now I've justified the philosophical relationship of the Arhenius equation to the rate equation for what K is and how it's related and how you could conjoin the two to get R, the R over the product, and then do this, and then you could calculate. Now this, you could cancel that unless you did natural logs. You wouldn't be able to cancel RR. It's because it's bound by the exponent. So sorry, excuse me. So that's how we link R equals, but the foundation comes from here, the thermodynamics law of 0 first, second, third, U equals QV, U equals kinetic energy plus potential energy, the rate equation R1 plus R2 equals P1, P2, P3, and then we examined the hydrogen fuel cell equation, the fuel cell equation here, and we then discussed this equation as well, the Haber process. And now I'm going to come to Nernst-Goldberg dynamics, the Nernst-Goldberg mechanism, the Nernst-Goldberg system. I call it system or dynamic because it is a system. It's describing and glorifying the calculational importance and the clinical importance of ionic exchange during active transport, facilitated diffusion, passive diffusion. So let me get my marker, bear with me please. So it would the processes that these equations are used for are active transport, facilitated diffusion, and passive diffusion, that are discussed in Fick's law, the Fick's law, which is quite mechanical, non-sentient to small changes, and then passive diffusion. Passive diffusion, and there's also another one. So that's against the gradient. That's and then you've got osmosis as well. Osmosis is diffusion of water basically, and then reverse osmosis as well. Reverse osmosis. And then that's against the gradient, minus m. That's positive gradient, and then that's positive m as well. And osmosis is positive m, and that's gradient is a bit dodgy there. So active transport, facilitated diffusion, passive diffusion, osmosis, and reverse osmosis is where you use this equation, CRT, concentration times rate, 8.31 times temperature. You use that, which is pressure, which is the same one as here, P equals CRT. Here in electrophysiology they use pi. Now I mean, you must have watched my videos on electrochemistry, which is why only now I've dealt with these two equations forming part of the Nernst-Goldberg system. The importance of these two equations is such that you know now what this is, the energy change, the Q, heat, and then you know R, you know T, and from my previous video you know this is the Faraday Constant, which is 96,500 coulombs per mole, and this is a number of moles. It could be 1 for silver, 3 for aluminium, and 2 for copper. And then this is the concentration of the ions outside the cell membrane, that's inside the cell membrane, and that's the Faraday Constant, and that's the oxidation number. So oxidation number. So there are two ways of calculating it. Now if we were to equalize it, actually equalize it, this is what it would look like. So it would look like minus RT over NF, and then Q equals RT over FZ whole multiplied by sorry, that should be and then so this is what it would look like if you equalized this equation 1